Good afternoon, everyone. I want to welcome you to another statistical class. Of course, statistics is like a story that goes on and on and on. The essence of today's topic is actually attributed to the fact that we need information that will translate into knowledge that will enable us to secure, understand our environment. Now, I remember on Monday, I walk you through what I call, graphical representation of qualitative data, where I display some kind of graphs that we use for the purpose. I also walk you through the graphical representation of quantitative data, and I told you the intention. But today, we actually want to move away from graphical representation to numerical representation. And we're going to be focusing on quantitative data. Now in the outline, of course, I'm going to talk about some measures. Okay, so I'm going to talk about measures like the measures of center. I'm going to talk about the measures of spread. I'm going to talk about measures of position. I'm also going to talk about measures of shape. And lastly, talk about outliers. Now, I need you to pay attention, because what we actually want to do today play a very key role in descriptive statistics. So these are the kind of measures that we use. Okay? Now, these measures, from measures of center all the way to measures of shape, they are interconnected measures, okay, that help us to have a comprehensive understanding of our data structure. They work hand in hand. Now, I will briefly give you the role of each of the measure before I actually dazzle into each of them. Now, the measure of center, the idea behind the measures of center is because there's variation, right? We have the data set, variation in data set. It could be data set on height, on weight, on blood pressure, on whatever data set variation exists. Then the idea of measures of center is, can we have a way to identify a particular data point that will represent others? I'm going to say that again. The measures of center, that we also call the measure of central tendency. We also call it the measures of location. Okay. The idea behind that is we actually want to figure out, we want to identify a particular common value, a typical value, a representative value, okay, among all the data set. Okay, we use mean. For that, we use median, we use mode. I'm actually going to walk you through when is it appropriate to use mean, when is it appropriate to use median, and when it is appropriate to use mode. Now, that is what the measure of center does. The measures of center is just to be able to identify one particular data point that is a good representative of the rest. The measure of spread, on the other hand, is talking about, okay, how far how far on average the rest of the observation is from the center. I'm going to say that again. When I say how far on average, I actually want to look at how they spread out. Are they, narrowly around the mean or widely around the mean? Okay. We also want to know that. So with that, we were talking about the measure of spread. The idea of, what we normally use, the range, the variance, the standard deviation, the coefficient of variation, we use that for that purpose. And I'm also going to identify situation where each of the measure is appropriate. The next one, the measures of position. Position. What do I mean? What is the intention here? The intention of the measures of position is to be able to locate or identify, the position a particular data point occupy in relation to the rest. I'm going to say that again. We want to identify the position a particular data point lies or fall in relation to the rest. Then we're going to use measures of position for that. We have the quartiles, we have the decile, we have the percentiles. That is what they do to locate a particular data point, okay, in relation to the rest, the position occupied. For instance, if somebody's exam score correspond to, let's say, for instance, 85 percentile. So what that means is that that person performed better than the 85% of the students that participated in the exam. Because of the variation in the world, we live in a world where we compare. If there is no variation, there is absolutely nothing to compare. Are you following? Good. Now I'm going to go to the measures of shape. You know what I'm doing now? I'm giving you the expectation on this because I know this is not your first time of seeing this. You've seen it before, but you don't really understand what is behind the scene. You don't really understand that. And that's why I'm trying to, point it out. Now the measures of shape. The measures of shape will enable us to know the distribution of the data, just like what we did on Monday. Is the data set normally distributed? Is the data set skewed? Why am I interested in that? Why am I interested in the distribution of the data set? I'm actually interested in the distribution of the data set because that will tell me whether the measures of central tendency, the measures of center I'm actually going to use. When to use mean is different from when to use median. So to use mean or median or mode, that depends on the distribution of the data set. You can see why I said they work hand in hand. So measures of shape talk about the distribution of the data set. I remember on Monday, I walk you through histogram and stem plot. With the histogram and stem plot, you will be able to know how the data set are distributed. Is it symmetric or skewed? Is it skewed to the right or skewed to the left? Finally, outliers. In any statistical analysis, we actually need to watch out for a particular data point that is not consistent with the rest. According to Benkamp in 1982, okay, an outlier is a data point that is not consistent with the rest, and of course, it could be damaging. Okay, now we need to be able to investigate, does that data point exist through error? like erroneous imputation or something else that require, further inquiry. We ask a lot of questions in science. Now I want to go into the, I've just given you our intention now. And I want to go back to the measure of Sarah. Now, the first one is actually mean. And let me tell you this. My data set is looking like this. I told you the other time, when you're collecting data on variable, or when you're collecting data, you need to be able to know what variable are you collecting data on. Statistically speaking, we use X, notation X, to represent the variable. My variable could be height, could be weight, could be blood pressure, could be income, could be whatever. Okay. Now, why do I have X1, S2 up to S3 up to Xn? Because I believe I'm taking a sample of observation N. It could be 20, it could be 50, it could be whatever. And what I'm gonna have as X1 will be different from X2. It's just like I'm checking your weight. Okay, that's what it means. Now I know there's going to be variation in weight, but you know what? I want to talk about the average weight of my students in my class. I know variation exists, but can I have a measure to identify just one data point that will represent every weight? Then using mean will requires you adding all the observation together. Okay, you're going to add the observation together and you divide by hand. Well, sum of x divided by hand. With that, you're going to get your mean. Then another idea here is that, okay, the median is going to say, I don't need to add my observation together. The only thing I only need to do is to first arrange my observation, whether in ascending order or in descending order. And after doing that, I'm actually going to go to the middle and I will identify the data point. Okay, that is what the median is talking about. But mode, on the other hand, said, you know what? I'm not going to add the observation and divide by the number. I'm not also going to arrange the observation, but what I'm going to be focusing on, I actually want to identify a particular data point that dominates others, which is what we call the most frequently occurring data point that is going to serve as a mode. You can see the three measures of Sarah. They are fantastic ideas, but they are not the same. Does that make sense? Okay, now you know about the mean, the median, the mode, but the question now is when should I use median? When should I use mode? When should I use mean? I needed to listen. I needed to listen. You know what? You know what happened? In the world, it's not as if our models are failing us. Our models are not failing us. We are the one that we're not doing the right thing. We are not doing the right thing when we are using the wrong statistical methodology for a particular situation. You are actually in this class to be able to figure out what is the appropriate statistical approach that I'm actually going to use for my problem or for a given problem. Now, let me tell you this. If you really want to know, okay, when to use mean, when to use median, when to use mode, then you should care about what we did on Monday. What do we do on Monday? On Monday, we try to figure out the we call that graphical representation of quantitative data. We're talking about quantitative right now. Now, the graphical representation, one of them talk about histogram, which is talking about the distribution. Now, let me tell you this. When I draw my histogram and the curve is normal, okay, I can use mean, I can use median, I can use mode, because they're all going to be the same when data set are normally distributed. But the best among them is mean. Okay, the best among them is mean when data set are normally distributed. But what if in a situation where I construct my histogram or my stem plot and I got a skewness? Maybe the distribution is skewed to the right or skewed to the left, then mean is not going to be an appropriate measure. Then the appropriate measure is actually going to be median. We use mean for symmetrical, curve. For when you see that your histogram is normal, okay, showing the normal curve. But when it is skewed, okay, we use median, not the mean. I'm going to tell you why. When I say skewed, either skewed to the right or skewed to the left. That is skewness. Skewness means, okay, departure of the distribution of data from normality. That's what skewness means. Skewness is a problem in statistics. Does that make sense? But the fact that it's a problem, we have a way of dealing with it. And that is the reason why when you care about Sarah, don't use mean when the distribution is skewed. Instead, use median. I'm going to go into an example now. I wanted to see the reason why calculating the mean and the median and the mode is not, may not give you the same values. But I've not said something about mode. But let me tell you this. We normally silent on mode in statistical analysis because of the fact that mode may not exist in a data set. There's possibility you don't have a particular data point that occur more frequently, like this one. If you take a look at this data set now, okay, there's no data point that is repeated. 0.3.7 up to 20.1. There's no one that is repeated. That is one of the reasons, because mode may not exist. And when mode exists, it could be more than one. Two mode is a problem. We call that bimodal. More than two mode is multimodal. That's a problem too. Okay, now, if you take a look at this data set, we compute the median, we compute the mean. The question now is, which one should we trust? Median is 1.6. Mean is 4.7. This is conflicting. Okay? Whenever you see a situation like this, to be able to know the one you're going to trust, then you need to go back to your histogram and look at the distribution. If your histogram is normally distributed, you follow the mean. If your histogram is skewed, don't trust your mean. Go with median. Does that make sense? Okay. Now, I'm going to go with the example. I'm going to go into mode example now. Oh my God. Even though we're silent on the mode is a measure of Sarah used in election. Election. You know in election? Okay? The eventual winner will be the most popular, right? And we said mode refer to as a particular data point that dominates. Take a look at this example now. The numbers of votes, okay, for candidate for mayor, and of course, we got to a candidate ABC. This is total numbers of votes they receive. Okay, now we're actually going to declare candidate C the winner because the candidate C is the most popular. The candidate C has the highest frequency. Does that make sense? So what we use here is mode. Like in here, we can't use mean. We can't use median. It doesn't make sense. Okay. Now, and at times, If the two candidates have the same number, is that not a problem? That's a bimodal, right? And in some states in the United States, like Georgia, they're going to say, okay, they're going to go for a runoff. Has anybody heard about runoff in politics? Oh, thank you so much. The first stage of election was not able to, decide a clear winner. I want to show you a picture now. Okay. I'll show you a picture right now. I need you to take a look at this guy here. Okay. You take a look at this guy now. This is a situation where we got one mode. You see the tallest one, right? Okay, that is a mode in this situation. It means this particular number here occur, the frequency is the highest. That's a mode. Okay, this is getting a mode from a graphical structure. Okay, now I want to show you bimodal now. Bimodal. Okay, situation where we got two mode. Oh my God, look at that. Two mode. Look at this guy. Look at this guy. Having two mode is more or less like having two captain in a ship. That could be problematic at times, Now, another one that I'm actually going to show you, multimodal, multi, okay? That is even more complicated. You have more than two mode. Take a look at the picture right now. Okay, can you see the picture right now? We got three mode here. Take a look at that. Okay, and it's complicated. Okay, now, which means if you want to take a decision here, okay, you are not likely going to choose one. You need a further analysis. You need something more appropriate. Okay, now, when to use mode, I told you the other time, mode is not a very useful measure. Okay, we normally silent on this, on mode, and I'm going to tell you why it's not. It is insensitive to large changes in data set. What is the meaning of that? Okay, this is the meaning. This guy is here. This guy is here. They're in the chemistry lab. They're taking measurement about chemistry, right? Maybe on acid. Maybe they are performing acid-based titration, and they're figuring out the titer value. This particular set of people here, they are economy students. They're working on income. The two of them have different data structure, but do you know they can have the same mode? Look at that. We have two different data sets. Even the distribution is not the same, as you can see, but they got the same mode. That doesn't make sense. Does that make sense? That doesn't make sense. Go ahead. I should say that one more time, right? I said mode, you could have two different data structure and they could have the same mode. Despite the fact that there are two different data structure. I mentioned some people having chemical readings. Some are working on dollars. The two that I said are not the same. That is why you can see the distribution here, not the same as well. So using mode here, it doesn't really make sense because this is giving that, they have the same mode. They have the same average. Okay. Now, now I need you to pay attention now. Let's say, for instance, I don't want to, maybe I don't have time to construct histogram. I don't have that time to construct the stem and leaf plot. What is another way to figure out the distribution of my data set? Another way to figure out the distribution of your data set is go ahead, compute the mean, compute the median, and compute the mode. And let me tell you this, when mean is greater than median, and median is greater than mode, then your data has a positive skewness. Can I say that one more time? Okay. If I don't want to care about constructing histogram, if I don't want to care about getting the stem and leaf plots, and I want to figure out the distribution of my data set, what I will advise you to do, calculate your mean, calculate your median, calculate your mode, then compare them. Situation where mean is greater than median and median is greater than mode, your data has a positive skewness. But what if in a situation where your mean is less than the median and the median is less than the mode, then you have a negative skewness. Oh, when do I have a normal? Where do I have no skewness? No skewness, having normality, that is when the mean, the median, and the mode, they are all equal. Does that make sense? It means the data that said that I showed you before, the mean was greater than the median, then that data set is positively skewed. Does that make sense? And that is what I'm trying to explain here. That's what I'm trying to explain here. And let me also tell you this. We don't use mean to figure out the center when the data set is skewed, because the skewness could be induced by the presence of outlier in the data. My PhD work that I defended in 2016 from the University of Ibadan, Nigeria. I think I also briefly, I had a scholarship to also present a work at the University of Oxford in the United Kingdom in 2015. That work was centered on outlier. How do we deal with outlier? Outlier is a problem. Outlier is a data point that could cause problem. Outlier induces skewness and it is sensitive to outliers. Wow. Why? How? Oh, when I want to compute the mean, I'm going to add all the observation, including the outlier. Definitely, that will affect results. Does that make sense? But if I want to use median, I'm going to rearrange the observations from the lowest to the highest. Outliers will never be in the middle. Outlier could be extremely low or extremely high. Does that make sense? And that is the reason why median is not sensitive to outlier, but mean is sensitive to outlier. Okay, now I'm gonna go right now. Gonna move. Oh my God, I like baseball. Take a look at this. What is happening now? What is happening here? Okay, New York Yankees baseball team, 2006. We decided to obtain the mean salary. We also obtain the median salary. Right now, the mean salary and the median salary are conflicting. And the question say, how possible? What is the direction of skewness? The direction of, okay, I want to award an extra credit. What is the direction of skewness? Positive, right? Send me a message for extra credit. Good job. Why positive? Because the mean is greater than the median. I don't even need to do histogram to be able to know that. I can tell from the mean and the median. Go ahead. Exactly. I'm gonna say, oh, that's a negative skewness. But what if in a situation where they're the same? Or they are approximately the same? Then I'm gonna say no skewness. Okay. Do you want to say my mind? Okay. It's normal. What do you want to say? You also want to say the same thing. You also want to say, what do you want to say? Okay, so you're speaking my mind. Also send me a message for extra credit when you are in my party. If you want to enjoy my party more, you answer my question and you get more than enough cookies. Statistical cookies and candies. Okay, let's keep going. Okay, now I don't joke with my extra credit. Whenever you have my extra credit, send me a message and keep track of that. At the end of the semester, we're going to add up how many extra credit point. Imagine somebody score 80 in exam, 80%, and somebody have a 20 point of extra credit. You can say, okay, you know what, professor, can you add my 20 to 80? Then you have 100%. That's where I do my stuff. Okay, now, you know what I want you to see now? I want us to go back to the Instagram and let us see where we can, let's see the relationship. Take a look at this guy. What is happening? Zero skewness. That's a normality, right? Can you see that? That's a normality, right? Now in this situation, the mean, median, and mode are going to be the same. Take a look at that. There's going to be center. Can you see center? Okay, because the center now, divide it into two equal parts. When you are able to divide that into two equal parts in such a way, the two halves are exactly the same. Of course, the mean, the median, and the mode are going to be the same. Does that make sense? Now, let's come to the positive skewness. Oh my God, look at the positive skewness. Okay, what do you see? Mean is greater than the median. And the median is greater than that. Look at 305. You can see that? If you come to the negative skewness, okay, reverse is the case. The mean is less than the median, and the median is less than that. Okay, we want you to be able to recognize this relationship. What are we doing at the moment? We're trying to get to know our data set, which we have not even answered a research question yet. Oh, we got some patient in our clinic right now. We've not started giving them medicine. We've not prescribed, but all what we're trying to do is for us to be able to know the direction of our intervention. We need to be able to understand our patient. So what we're doing right now, we're trying to get to know our data set. Does that make sense? Okay. Now we want to go to another measure. Why do we need this measure? You know, we can't talk about this measure without referring to the measure of Sarah. We're done with the measure of Sarah. The takeaway from the measure of Sarah is actually to figure out a particular data point that represents the rest. But what is our intention here in the measures of spread? We actually want to know on average how the data spread out around the center. Are they very close to the center or far away from the center? Okay, want to see how narrowly, they spread out. They narrowly spread out or they spread out widely? If we want to do that, we're going to talk about measures of spread. The measures of spread is very, very important in statistical analysis. Now, one of them is the range, the other one is the variance, the other one is the standard deviation, and another one is the coefficient of variation. But you know what? What is the range? The range is the difference between the highest and the lowest. The more the more the range, then the more the degree of variation. And when the data spread out so much, you know what happened? Then the mean, the data point that you choose to represent may not be a good representative of the others. Oh, let me look at this in politics. Let's say somebody is representing this constituency now, and it's in the Congress, it's in Washington, right? For the person to be able to represent this consistency well in Minnesota, that particular person must not be far away from the people. He has to organize towns or meeting with them to know what people need. But if it is far away from the people, because that person is an average value representing people. So when the range is large, the variation is large. But what is the limitation of the range? as a measure of spread. Go ahead. Yeah, what is a limitation? Okay, yeah, that's a good one. That's you very close. But the question now is, why is it that we cannot trust range as a measure? It's like, what do I need to see if I cannot trust a judge? Exactly. We don't know the spread. That's one of it. Go ahead. That's a nice one. That's another nice one. Yeah. Okay. That's another nice one. Go ahead. That's a nice one. If you mention outliers, because if outlier is present in the data set, then range would have used the outlier point, because outlier is either it's extremely low or it's extremely high. Range is sensitive to outlier. Therefore, range is not a good measure if the distribution is skewed. And what may induce the skewness? Outlier. Does that make sense? Wonderful contribution. Now we have another measure that we call variance and standard deviation. But let me tell you this. When we say variance, we got two types of variance. We have a population variance. We have a sample variance. We have a population standard deviation. We have a sample standard deviation. Let me tell you the difference between the two. In the population variance that we call sigma squared, we divide by n when we subtract the mean from the respective data point. Okay. Now, why are we squaring? Oh, we're squaring because we actually want positive. We're trying to tell the world, if I have 0 at the center and I have a +3 to the right, -3 to the left. Oh, when I square -3 and I square +3, they all give 9. They give the same. What does that mean? Oh, -3 and +3 they have equal distance to the center. That is the meaning. But let me tell you, so now that is why we actually squared, and at the end of the day we have sigma squared, which is the variance. The variance tells us on average how far apart is the the mean, the data from the respective, from the mean. How far on average is the data point from the mean, or how far on average is the mean from the respective observation? Does that make sense? How far on average is the mean from the respective observation? How far is this legislator representing us? How far it is to the people is representing? Okay, now that is what this guy is trying to say. Now, why do we need a standard deviation? Because the variance has a square unit. If I'm working with dollar, the unit of individual observation is the unit of the mean. If I'm working with dollar, the mean is also going to be in dollar. If I'm working with variance, oh my God, the variance is going to be dollar squared. That doesn't make sense. Then what are we going to do? So which means variance is not in the same, variance doesn't have the same unit as the mean. Now, what mathematical manipulations are we going to do to make sure, that are the same unit as the mean is to find the square root? That is the essence of finding the square root. In statistical analysis, we focus more on the standard deviation, but you know what? There is no way I will be able to get to the standard deviation without knocking at the door of the variance. Does that make sense? Okay. But you know what? In two of this, we divide it by n. That is when we're working with the whole data set in the population, but we're never going to do that. You know what we're going to do? We're going to be working with sample. When we're working with a sample, okay, we actually is going to be divided by n minus 1. And what is the meaning of the n minus 1? Where am I subtracting 1? I'm going to tell you now. Subtracting 1 means that n minus 1 means degree of freedom. What is the meaning? Oh, if I have 10 observations, before looking for spread, I've already computed the mean. How many more? So which means I'm not going to have 10 variations. It is not all the data that will vary anymore. Out of 10 data that I have, it's only 9 that will vary. That is what we call degree of freedom. You're granting freedom. If you have 50 observations, you're only going to grant freedom to 49 because you've already computed your mean. Before coming to this, we have already mean is this mu. Does that make sense? And that is the reason why we divide by n minus 1. The n minus 1 is the number of data points that we allow to vary. It is not all of them that will vary anymore when the mean is already computed. Okay, now the next thing now, let's start applying that. Political ideology. We have 9 data points, which is a sample, right? Okay, and the data point, we got 2, 3, 7, 5, 6, 7, 5, 6, 4. Okay, I'm not going to ask you to do this manually. Of course, that is the essence of the lab. We have our code that will do all of that. Now, I find the mean of this data set, which is y bar. Oh, sorry, I'm supposed to say x bar. My bad, because I've already defined my data set to be x. So that should be x bar instead of y bar. When a variable has a bar, that indicates the mean. Does that make sense? I added all this observation. I divide by 9. I got that. Now, the next thing I'm going to do, I want to get a sample variance. I'm just going to be subtracting the mean from each of the observation. Then I'm going to square that. Then I will divide by number of observation minus 1. And after that, I got a sample variance. Then I take the square roots of that to get a sample standard deviation, because the units of the standard deviation and the mean are the same, but the variance has a square unit. And that's why we normally focus more on the standard deviation. Now, going by the properties of standard deviation, let me tell you, when the standard deviation is 0, okay, or that means there's no variation in your data set. Okay, like all your data points are the same. That is not going to be possible. So your standard deviation can be 0 or greater than 0. When you compute and your standard deviation is negative, you are wrong. When your variance is negative, you are wrong. There shouldn't be any reason to get negative, because don't forget you squared. Okay. Now, the next thing I'm going to, and when standard deviation increases, amount of variation around the mean also increases. We don't want that. If the variation around the mean increases, then the mean is not, that mean may not be a good representative. Does that make sense? Okay. Now, I want to go into what is another way in statistics. If I really want to know, whether the data set that I have follow normal distribution, there's something that we call empirical rule. Okay, all what I just need to do with the empirical rule is this. I need to compute z-score. Z-score. What do I mean by z-score? I'm actually going to have the observation minus the mean divided by the standard deviation. So it means when I have data set, I first get the mean, I get the standard deviation, then I can get a z-score. What I'm going to be doing is to be subtracting the mean from the respective data point divided by standard deviation. That will give me a z-score. What is the meaning of a z-score? Oh, the meaning of a z-score is we want to know the number of standard deviation away from the mean. Now, if if z-score equal to 1, let's say for instance, you compute is your z-score is equal to 1. You know the meaning? It means the number of standard deviation above the mean is 1. If it is -1, then 1 below the mean. Okay, and you know what? If your data set is normal, okay, we've been able to establish 68% of your data will fall within 1 standard deviation of the mean. 95% of your data will fall within 2 standard deviation of the mean. Then nearly all data, or about 99.75% of data will fall within 3 standard deviation of the mean. So by considering all of that, our intention is to be able to see how far can we have a way to investigate how far a particular values away from the mean. The mean is a center. In a stochastic environment, we always have a threshold. We want to see whether something go beyond threshold or something go below threshold. Does that make sense? Okay. Lastly, before I go, coefficient of variation. If I want to have a measures of consistency, when do we use coefficient of variation? Oh my God, I got 2 different set of data, and I want to know which one is more dispersed, okay, or which one is less dispersed. This particular measure is very close in stock returns analysis because the measure of risk in the stock return is standard deviation. I'm going to say that again. Standard deviation, okay, is a measure of risk in stock analysis. Okay, now what I'm going to do is I'll compute the coefficient of variation. You know, computing the coefficient of variation, I need a standard deviation and I need the average. When I find the ratio of that, that is going to give me the coefficient of variation in percentage. The more the coefficient of variation, we want a situation where the CV is going to be so low. If the CV is so low, then it is there's consistency. If the CV is so high, then there's more variability, more risk. Okay, and that is take a look at this. I'm going to give you this an example. We want to compare 2 groups of data. We want to know which one is more consistent. The one that is more consistent, consistency as a property in statistical analysis has to do with the low values of coefficient of variation. Now, at the end of the day, take a look at this. We get this guy now. You have this data set. Okay, a sample of newborn infant had a mean weight of 6.2 pounds with a standard deviation of 1 pound, and a sample of 3-month-old children had a mean. You know, you're comparing a newborn infant with 3-month-old children, and you have information about the mean, you have the information about the standard deviation, and your intention is not to compare the average. Your intention is actually to compare whether which of the 2 that I said is more consistent and the one that is more variable. Okay, now I'm going to show you what we have before we go. Now, what we have is this. Take a look at that. The first one gives 16%. The second one gives 40%. The one for the 3-month-old has a lower CV. That is more consistent. The higher one is more variable. This is where I'm going to stop today. Okay, any question? Okay, go ahead. Exactly. The more variable, the more spread. And that is not good. We may not necessarily know what could be the problem, but one of the problem could be maybe outlier cause that. Yeah. Okay. Bye for now, everyone. The what? Oh, the arrow link. Oh, yeah. Oh, did you? I think by now you should have. Have you attended lab for this week? Your yeah. The link is still up. Thank you. Do I message you? I answer. Yeah. You are messaging you.
I have a question on the assignment, like the assignment zero.
Okay.
So you said put them into different pages.
Yeah.
How would you like this format? Just each answer and question is its own page.
I know. It's gonna be on the same page.
So just like that, and then
Just like that.
and then
Yeah, that should be fine.
okay, thank you.
Also, the same. If we wanted more like problems to solve, do we have to do it off the book?
Yeah, that's why you have the book. So
Okay.
you just make sure you solve problem within the chapter for the week.
Okay. And when will we have the first assignment?
That will be on Sunday. You have assignment 0 now, due on Sunday.
Yeah.
Then the real assignment 1.
Yeah,
starting on Sunday.
Okay.
I'm gonna be doing it for weeks.
Okay. So once a week then?
Yeah, once a week.
Okay.
Yeah, just one assignment.
Thank you.
You're welcome.
Okay. All right. Yeah, you record your lecture.
It's on. Okay, let me do this. Let me stop this. Yes.
Guys, he's super like passionate. I call it something.